Distillation is a process of separating the component substances from a liquid mixture by selective evaporation and condensation. Distillation may result in essentially complete separation, or it may be a partial separation that increases the concentration of selected components of the mixture. In either case, the process exploits differences in the volatility of the mixture's components. In industrial chemistry, distillation is a unit operation of practically universal importance, but it is a physical separation process and not a chemical reaction. Commercially, distillation has many applications. For example, in the fossil fuel industry, distillation is a major class of operation in obtaining materials from crude oil for fuels and for chemical feedstocks. Distillation permits separation of air into its components, notably oxygen, nitrogen, and argon, for industrial use. In the field of industrial chemistry, large ranges of crude liquid products of chemical synthesis are distilled to separate them, either from other products, or from impurities, or from unreacted starting materials. Distillation of fermented products produces distilled beverages with a high alcohol content, or separates out other fermentation products of commercial value. An installation for distillation, especially of alcohol, is a distillery. The distillation equipment is a still history. Aristotle wrote about the process in his Meteorologica, and even that ordinary wine possesses a kind of exhalation, and that is why it gives out a flame. Later evidence of distillation comes from Greek alchemists working in Alexandria in the 1st century AD. Distilled water has been known since at least c. 200, when Alexander of Aphrodisias described the process. Distillation in China could have begun during the Eastern Han Dynasty, but archaeological evidence indicates that actual distillation of beverages began in the Jin and Southern Song dynasties. A still was found in an archaeological site in Qinglong, Hebei province, dating to the 12th century. Distilled beverages were more common during the Yuan dynasty. Arabs learned the process from the Alexandrians and used it extensively in the chemical experiments. Clear evidence of the distillation of alcohol comes from the school of Salerno in the 12th century. Fractional distillation was developed by Taddeo Alderotti in the 13th century. In 1500, German alchemist Hieronymus Braunschweig published Liber der Art Destillandi, the first book solely dedicated to the subject of distillation, followed in 1512 by a much expanded version. In 1651, John French published The Art of Distillation, the first major English compendium of practice, though it has been claimed that much of it derives from Braunschweig's work. This includes diagrams with people in them showing the industrial rather than bench scale of the operation. As alchemy evolved into the science of chemistry, vessels called retorts became used for distillations. Both alembics and retorts are forms of glassware with long necks pointing to the side at a downward angle, which acted as air-cooled condensers to condense the distillate and let it drip downward for collection. Later, copper alembics were invented. Riveted joints were often kept tight by using various mixtures, for instance a dough made of rye flour. These alembics often featured a cooling system around the beak, using cold water for instance, which made the condensation of alcohol more efficient. These were called pot stills. Today, the retorts and pot stills have been largely supplanted by more efficient distillation methods in most industrial processes. However, the pot still is still widely used for the elaboration of some fine alcohols such as cognac, Scotch whiskey, tequila, and some vodkas. Pot stills made of various materials are also used by bootleggers in various countries. Small small pot stills are also sold for the domestic production of flour, water, or essential oils. Early forms of distillation were batch processes using one vaporization and one condensation. Purity was improved by further distillation of the condensate. Greater volumes were processed by simply repeating the distillation. Chemists were reported to carry out as many as 500 to 600 distillations in order to obtain a pure compound. In the early 19th century, the basics of modern techniques, including preheating and reflux, were developed, particularly by the French. Then in 1830 a British patent was issued to Eneas Coffey for a whiskey distillation column, which worked continuously and may be regarded as the archetype of modern petrochemical units. In 1877, Ernest Solvay was granted U.S. patent for a tray column for ammonia distillation, and the same and subsequent years saw developments of this theme for oil and spirits. With the emergence of chemical engineering as a discipline at the end of the 19th century, scientific rather than empirical methods could be applied. The developing petroleum industry in the early 20th century provided the impetus for the development of accurate design methods such as the McCabe-Thiele method and the Fensky equation. The availability of powerful computers has also allowed direct computer simulation of distillation columns. Applications of distillation. The application of distillation can roughly be divided in four groups. Laboratory-scale industrial distillation, distillation of herbs for perfumery and medicinals, and food processing. The latter two are distinctively different from the former two in that in the processing of beverages and herbs, the distillation is not used as a true purification method but more to transfer all volatiles from the source materials to the distillate. The main difference between laboratory-scale distillation and industrial distillation is that laboratory-scale distillation is often performed batch-wise, whereas industrial distillation often occurs continuously. In batch distillation, the composition of the source material, the vapors of the distilling compounds and the distillate change during the distillation. In batch distillation, a still is charged with a batch of feed mixture, which is then separated into its component fractions, which are collected sequentially from most volatile to less volatile, with the bottoms removed at the end. The still can then be recharged and the process repeated. In continuous distillation, the source materials, vapors, and distillate are kept at a constant composition by carefully replenishing the source material and removing fractions from both vapor and liquid in the system. This results in a better control of the separation process. Idealized distillation model. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid equals the pressure around the liquid, enabling bubbles to form without being crushed. A special case is the normal boiling point, where the vapor pressure of the liquid equals the ambient atmospheric pressure. It is a common misconception that in a liquid mixture at a given pressure, each component boils at the boiling point corresponding to the given pressure, and the vapors of each component will collect separately and purely. This, however, does not occur even in an idealized system. Idealized models of distillation are essentially governed by Rathould's law and Dalton's law, and assume that vapor-liquid equilibria are attained. Rathould's law states that the vapor pressure of a solution is dependent on 1. The vapor pressure of each chemical component in the solution, and 2. The fraction of solution each component makes up a Ka, the mole fraction. This law applies to ideal solutions, or solutions that have different components but whose molecular interactions are the same as are very similar to pure solutions. Dalton's law states that the total pressure is the sum of the partial pressures of each individual component in the mixture. When a multi-component liquid is heated, the vapor pressure of each component will rise, thus causing the total vapor pressure to rise. When the total vapor pressure reaches the pressure surrounding the liquid, boiling occurs and liquid turns to gas throughout the bulk of the liquid. Note that a mixture with a given composition has one boiling point at a given pressure when the components are mutually soluble. A mixture of constant composition does not have multiple boiling points. An implication of one boiling point is that light components never cleanly boil first. At boiling point, all volatile components boil, but for a component, its percentage in the vapor is the same as its percentage of the total vapor pressure. Lighter components have a higher partial pressure and thus are concentrated in the vapor, but heavier volatile components also have a partial pressure and necessarily evaporate also, albeit being less concentrated in the vapor. Indeed, batch distillation and fractionation succeed by varying the composition of the mixture. In batch distillation, the batch evaporates, which changes its composition. In fractionation, liquid higher in the fractionation column contains more lights and boils at lower temperatures. Therefore, starting from a given mixture, it appears to have a boiling range instead of a boiling point. Although this is because its composition changes, each intermediate mixture has its own singular boiling point. The idealized model is accurate in the case of chemically similar liquids, such as benzene and toluene. In other cases, severe deviations from Raoult's law and Dalton's law are observed, most famously in the mixture of ethanol and water. These compounds, when heated together, form an azeotrope, which is a composition with a boiling point higher or lower than the boiling point of each separate liquid. Virtually all liquids, when mixed and heated, will display azeotropic behavior, although there are computational methods that can be used to estimate the behavior of a mixture of arbitrary components. The only way to obtain accurate vapor-liquid equilibrium data is by measurement. It is not possible to completely purify a mixture of components by distillation, as this would require each component in the mixture to have a zero partial pressure. If ultra-pure products are the goal, then further chemical separation must be applied. When a binary mixture is evaporated and the other component, e.g., a salt, has zero partial pressure for practical purposes, the process is simpler and is called evaporation in engineering. Batch distillation, heating an ideal mixture of two volatile substances A and B in a batch distillation setup until the mixture is boiling, results in a vapor above the liquid which contains a mixture of A and B. The ratio between A and B in the vapor will be different from the ratio in the liquid. The ratio in the liquid will be determined by how the original mixture was prepared, while the ratio in the vapor will be enriched in the more volatile compound A. The vapor goes through the condenser and is removed from the system. This in turn means that the ratio of compounds in the remaining liquid is now different from the initial ratio. The result is that the ratio in the liquid mixture is changing, becoming richer in component B. This causes the boiling point of the mixture to rise, which in turn results in a rise in the temperature in the vapor, which results in a changing ratio of A/B in the gas phase. This results in a slowly changing ratio at B in the distillate. If the difference in vapor pressure between the two components A and B is large, the mixture in the beginning of the distillation is highly enriched in component A, and when component A has distilled off, the boiling liquid is enriched in component B. Continuous distillation. Continuous distillation is an ongoing distillation in which a liquid mixture is continuously fed into the process and separated fractions are removed continuously. continuously as output streams occur over time during the operation. Continuous distillation produces a minimum of 2 output fractions, including at least one volatile distillate fraction, which has boiled and been separately captured as a vapor, and then condensed to a liquid. There is always a bottoms fraction, which is the least volatile residue that has not been separately captured as a condensed vapor. Continuous distillation differs from batch distillation in the respect that concentrations should not change over time. Continuous distillation can be run at a steady state for an arbitrary amount of time, for any source material of specific composition. The main variables that affect the purity of products in continuous distillation are the reflux ratio and the number of theoretical equilibrium stages, in practice determined by the number of trays at the height of packing. Reflux is a flow from the condenser back to the column, which generates a recycle that allows of better separation with a given number of trays. Equilibrium stages are ideal steps where compositions achieve vapor-liquid equilibrium, repeating the separation process and allowing better separation given a reflux ratio. A column with a high reflux ratio may have fewer stages, but it refluxes a large amount of liquid, giving a YE column with a large hold-up. Conversely, a column with a low reflux ratio must have a large number of stages, thus requiring a taller column. General improvements. Both batch and continuous distillations can be improved by making use of a fractionating column on top of the distillation flask. The column improves separation by providing a larger surface area for the vapor and condensate to come into contact. This helps it remain at equilibrium for as long as possible. The column can even consist of small subsystems which all contain an enriched boiling liquid mixture, all with their own vapor-liquid equilibrium. There are differences between laboratory scale and industrial scale fractionating columns, but the principles are the same. Examples of laboratory scale fractionating columns include air condenser, Vigro column, packed column, spinning band distillation system.